Take a deep breath in, and as you exhale, let your body settle into the quiet weightlessness of this moment. We are leaving the earthly atmosphere behind, drifting effortlessly into the comforting void of deep space, setting our sights on a marvel of cosmic architecture. Just 39.6 light-years away from our solar system, nestled within the borders of the constellation Aquarius, lies a planetary system that has fundamentally changed our understanding of the universe. Here is something remarkable to consider as you float through the dark. In May of 2016, and then with a major follow-up announcement in February of 2017, astronomers revealed the existence of 7 Earth-sized planets orbiting a single star. They named this system TRAPPIST-1. The name itself is an acronym for the Transiting Planets and Planetesimals Small Telescope, the ground-based observatory in Chile that first noticed the rhythmic dimming of this distant star. As you glide across the light years, imagine the vast, silent ocean of space parting for you, guiding you toward a faint, welcoming glow in the cosmic dark. As we arrive, the first thing you might sense is a profound shift in light and temperature. The star at the center of the TRAPPIST-1 system is not a blinding golden sphere like our Sun. It is an ultra-cool red dwarf star, scientifically classified as an M-type dwarf. Its surface temperature burns at roughly 2,550 Kelvin, or about 4,130 degrees Fahrenheit. While that might sound incredibly hot, it is less than half the temperature of our own Sun, which blazes at nearly 5,800 Kelvin. Because of this relatively cool temperature, the TRAPPIST-1 star does not emit the harsh, bright white light we are used to. Instead, it bathes its surrounding space in a deep, soothing ruby light, dominated by infrared radiation. Imagine floating in a space illuminated by the gentle, glowing embers of a dying fire, a warm, salmon-red luminescence that wraps around you like a heavy, comforting blanket. This star is remarkably small. It is only slightly larger than the planet Jupiter, with a radius about 11% that of our Sun. Yet, despite its modest physical footprint, it contains roughly 8% of the mass of our entire Sun. This means the star's matter is packed densely together by the sheer, unyielding force of gravity. Because it is so small and cool, this red dwarf consumes its hydrogen fuel at an incredibly slow, deliberate pace. Consider the profound peace of this fact. While our Sun has a total lifespan of about 10 billion years, TRAPPIST-1 will continue to burn steadily for trillions of years. It will outlive our solar system, serving as a quiet, eternal beacon of warmth in the universe long after other stars have faded into darkness. Drawing closer to the star, you can begin to perceive the magnificent clockwork of its 7 planets. They are named methodically, simply using letters from B through H, with TRAPPIST-1b being the innermost world and TRAPPIST-1H the furthest. What makes this system feel so cozy, so intimate, is its unbelievable scale. The entire TRAPPIST-1 planetary system is incredibly compact. In fact, all 7 of these Earth-sized worlds orbit closer to their star than Mercury orbits our Sun. If you were to drop this entire system into our solar neighborhood, it would comfortably fit well within the orbit of our innermost planet. Because they are huddled so close to their host star, these planets move with breathtaking speed. A single year on TRAPPIST-1b, the time it takes to complete one full orbit around the star, lasts just 1.5 Earth days. Even the outermost planet, TRAPPIST-1H, completes its year in a mere 18.7 Earth days. Yet, despite this rapid transit, there is no chaos here. There is only a smooth, silent ballet of gravity. As you observe their motion, you might almost feel a rhythmic pulse, a cosmic heartbeat echoing in the vacuum. This is because the planets of TRAPPIST-1 are locked in a near-perfect orbital resonance. Their gravitational pulls have gently nudged each other over billions of years into a beautifully synchronized dance. The resonance is a mathematical marvel. For every 8 orbits completed by the innermost planet, the second planet completes exactly 5, the third completes 3, and the fourth completes 2. This forms a chain of ratios, 8 to 5, 5 to 3, 3 to 2, that continues through the entire system. It is a literal harmony of the spheres. If you were to assign a musical note to each planet as it passed its neighbor, the system would play a resonant, repeating chord. It is a self-stabilizing rhythm that keeps the planets from colliding, an eternal metronome ticking away in the dark. Let yourself drift downward now, lowering your awareness toward the surface of one of these middle worlds. At least 3, and possibly 4, of these planets, specifically D, E, F, and G, rest firmly within the star's habitable zone. This is the delicate orbital distance where the ambient heat is just right, allowing for the possibility of liquid water to pool on a planet's surface. As you imagine setting foot on one of these rocky spheres, you would immediately notice a strange, mesmerizing phenomenon. Because these planets orbit so incredibly close to their star, the intense gravitational pull has likely left them tidally locked. Tidal locking occurs when a planet's rotation on its axis takes the exact same amount of time as its orbit around the star. This means that one side of the planet is permanently fixed, facing the red sun, locked in an eternal baking day. The opposite side faces away, staring out into the freezing, infinite night, never knowing the warmth of dawn. But there is a gentle middle ground. Imagine standing on the Terminator line, the permanent twilight zone that encircles the globe, dividing the light hemisphere from the dark. Here, the sun never rises and never sets. It simply hovers perpetually on the horizon, casting long, dramatic shadows across the landscape. The sky above you is a gradient of deep, dusky crimsons and purples. You can almost feel the temperature gradient on your skin, a cool, refreshing breeze flowing from the icy night side, meeting the gentle, warming currents blowing in from the sunlit hemisphere. This permanent twilight could be the perfect cradle for life, a place of perpetual sunset where the temperature remains endlessly comfortable. The texture of this world might be surprisingly familiar, yet wonderfully alien. Scientific measurements of the planet's masses and volumes have allowed astronomers to calculate their densities. These calculations reveal that they are rocky, terrestrial worlds, much like Earth, Venus, or Mars. However, the data suggests that some of these outer planets are remarkably rich in volatile materials. Astronomers estimate that up to 5% of the mass of some TRAPPIST-1 planets could be made entirely of water. To put that staggering number into perspective, water makes up only about 0.02% of the Earth's mass. This means a TRAPPIST-1 planet could hold up to 250 times more water than all of Earth's oceans combined. Picture what that might look like as you stand on the shoreline of a global ocean under a red sky. The waves rolling onto the rocky beach would be heavy, moved by gravitational forces uniquely their own. You might sense the thick, misty atmosphere clinging to the water's surface, reflecting the dim infrared glow of the eternal twilight. The air might feel damp and cool, filled with the quiet, rhythmic sound of an alien tide. Now, look up at the sky. Because these 7 planets are packed so tightly together, the distances between them are mere fractions of the distances we are used to in our solar system. At their closest approach, Neighboring planets are only a few million miles apart. If you were standing on the surface of one TRAPPIST-1 world, you would not see the other planets as tiny, distant points of twinkling light, the way we see Mars or Jupiter from Earth. Instead, the neighboring planets would loom massive and majestic in the sky. Some would appear up to twice as large as the full moon does from Earth. Imagine that breathtaking vista, a massive textured sphere hanging silently in the perpetual sunset. Its surface features, perhaps vast cloud bands or sprawling oceans, visible to the naked eye. You would be able to watch them slowly phase from crescents to full spheres as they completed their rapid orbits around the red star. The sky would be a slowly shifting gallery of giant worlds, drifting by in a quiet gravitational procession. This is the beauty of TRAPPIST-1. It is a system defined by its closeness, its warmth, and its eternal rhythmic stability. There is a deep comfort in knowing that such a place exists, a snug family of planets huddled around a gentle red ember, spinning in perfect musical harmony. As you float here, caught in the twilight of an endless sunset, you can let go of the fast-paced, erratic energies of our own world. You can simply exist in this quiet corner of the Aquarius constellation, feeling the soft pull of gravity, bathed in the infrared warmth of an ancient star. Every orbit here is a promise kept by the laws of physics. Every planetary passing is a silent note in a song that will play for trillions of years. Let the harmony of these 7 worlds wash over you, steadying your pulse, matching the slow, predictable clockwork of the cosmos. As you drift in the gentle pull of this celestial dance, allow yourself to sink deeper into the beauty of the dark, feeling completely held by the vast, interconnected tapestry of space. As we continue to observe this quiet, synchronized procession of worlds, it is deeply grounding to consider how humanity first reached out into the dark to find them. Long before these 7 terrestrial spheres were a celebrated discovery, this system was nothing more than an obscure sequence of letters and numbers in an astronomical database. For decades, it was simply known as 2MASS J 2306928-0502285. It sat unnoticed in the constellation of Aquarius, just a faint, unassuming smudge on our celestial maps. To truly appreciate the serenity of this system, we must look at the threshold of its existence. This tiny red orb barely possesses the physical requirements to be a star at all. Astronomers have measured its mass to be exactly 0.089 solar masses. In the mechanics of the cosmos, the absolute minimum mass required for a celestial body to ignite and sustain hydrogen fusion in its core is between 0.075 and 0.08 solar masses. Anything smaller becomes a brown dwarf, a dark, cooling sphere of gas, often called a failed star. The host of the TRAPPIST-1 system sits just above this critical boundary. It squeezed just enough matter together to ignite its internal furnace, succeeding in the darkest depths of space to become a quiet, enduring source of light. Notice how delicate that balance is. Because it is so small, its light is impossibly dim from our vantage point on Earth. To find the planets hidden within its glow, astronomers relied on a technique known as transit photometry. Think of this process like watching a tiny moth flutter across a distant street lamp on a foggy night. When a planet crosses directly between its host star and our telescopes, it blocks a microscopic fraction of the starlight. For TRAPPIST-1, this rhythmic dip in brightness is incredibly subtle, often registering as less than a 1% decrease in the star's total luminescence. The initial breakthrough came from a robotic telescope at the La Silla Observatory, perched high in the arid mountains of Chile. In May of 2016, researchers studying these minute shadows announced the discovery of just 3 planets, initially designated as B, C, and D. But the story did not end there. The heavens demand patience, and human ingenuity answered. Later that same year, humanity turned the Kepler Space Telescope toward Aquarius. During a specific observation window, designated as Campaign 12 of the K2 mission, Kepler monitored this single faint star continuously for 74 straight days. Following this, the Spitzer Space Telescope was called upon to join the silent vigil. Spitzer pointed its highly sensitive lens at the star for an astounding 500 consecutive hours. Imagine that level of focused stillness, a machine drifting in the freezing vacuum of space, staring unblinkingly at a single point of light for more than 20 days and nights, simply waiting for the shadows of planets to pass by. This patience yielded magnificent results. Spitzer's 500-hour observation revealed the remaining 4 worlds, completing the family of 7. The choice to use Spitzer was a stroke of scientific brilliance because it was designed specifically as an infrared telescope. This is vital because the TRAPPIST-1 star emits a staggering 95% of its energy in the invisible infrared spectrum. Where optical telescopes see only a faint red glimmer, an infrared lens sees a brilliant, shining beacon of heat. You allow your mind to absorb the deep historical context of this stellar classification. Our awareness of these ultra-cool red dwarfs has been slowly expanding over centuries. The very first red dwarf was catalogued long ago, in 1753, by a French astronomer named Nicolas Louis de Lacaille, observing from the Cape of Good Hope. His discovery, known as Lacaille 8760, opened our eyes to a new kind of celestial body. In the centuries since that night in 1753, modern astronomy has systematically mapped the heavens, leading to a stunning realization. Red dwarfs are not rare anomalies. In fact, they make up an estimated 73% of all the stars in the Milky Way galaxy. The quiet, glowing embers are the silent majority of our universe. What is happening now, as we study these stars, is a revolution in how we measure deep time. The TRAPPIST-1 system is unimaginably ancient. By carefully analyzing the speed at which the star rotates on its axis, astrophysicists have calculated its age to be roughly 7.6 billion years. Compare that to our own solar system. Our Sun, the Earth, and all the planets we know intimately have only existed for about 4.6 billion years. This means the soft red glow we are observing had already been radiating into the cosmic dark for 3 billion years before the Earth even began to form from a swirling disk of dust. It is a system steeped in the quiet grandeur of antiquity. As you picture these 7 ancient worlds orbiting their ancient sun, you might wonder how we know their exact weights and densities if we have only ever seen their shadows. The answer lies in a beautiful gravitational conversation. Scientists utilize a method called transit timing variations, or TTV. Because the TRAPPIST-1 planets are packed so closely together, their individual gravitational fields constantly pull and tug on one another as they pass in the night. This gentle tug of war acts like an invisible tether, causing the planets to speed up or slow down ever so slightly. As a result, a planet might cross in front of the star a few minutes early or a few minutes late. By measuring these minute discrepancies, these tiny variations in the transit timetable, physicists can calculate the exact gravitational mass of each planet. It is a masterclass in cosmic deduction, mapping the invisible forces of nature through the rhythm of shadows. Recently, our instruments have grown even more refined. In 2023, the James Webb Space Telescope turned its massive, gold-plated mirrors toward the TRAPPIST-1 system. Utilizing an incredibly sophisticated piece of technology called the Mid-Infrared Instrument, or MIRI, the telescope focused intensely on the innermost world, TRAPPIST-1b. Rather than just waiting for a shadow, MIRI was able to measure the actual thermal emission, the physical heat, radiating off the rocky day side of the planet. The data returned to Earth showed a daytime surface temperature of precisely 500 Kelvin, which translates to roughly 440 degrees Fahrenheit. This single measurement spoke volumes. By confirming a temperature of 500 Kelvin, astrophysicists deduced that TRAPPIST-1b likely lacks a thick carbon dioxide-rich atmosphere. If a dense atmosphere were present, it would act like a global circulatory system, distributing the heat around the planet and lowering that peak daytime temperature. Instead, the heat remains locked on the day side, baking the bare rock in the eternal noon of the tidally locked sphere. It is a stark, silent landscape, bathed in infrared radiation, entirely undisturbed by wind or weather. Deep within the structure of this system, there is another subtle clue regarding its formation. Spectroscopic analysis has determined that the star's metallicity, which is a measure of the abundance of elements heavier than hydrogen and helium, is approximately 109% that of our own Sun. This means the primordial cloud of gas and dust that collapsed to form TRAPPIST-1 7.6 billion years ago was slightly richer in heavy elements, like iron and silicon. This dense, mineral-rich environment provided the perfect foundational building blocks necessary to forge not just one, but 7 terrestrial, rocky worlds. There is an immense stillness in understanding these mechanics. We are not just looking at a collection of rocks in space. We are observing a finely tuned, ancient mechanism. From the precise 0.089 solar masses that ignited the star, to the 500-hour patient stare of an infrared lens, to the subtle gravitational tugs delaying a transit by mere minutes, everything operates according to an unbroken physical rhythm. Sink into the comfort of this enduring order. The slow dance of these planets has continued uninterrupted for billions of years before we developed the glass and mirrors to see them, and it will continue for trillions of years after. We are simply quiet witnesses to their passage, floating in the warm red light of an ancient ember, anchored by the beautiful, predictable mathematics of the deep cosmic ocean. To understand the architecture of this ancient, perfectly balanced mechanism, we can anchor our perspective by looking at objects we hold in our hands every day. The physical scale of the TRAPPIST-1 system defies our traditional expectations of what a planetary neighborhood should look like. Picture a standard basketball resting on the floor of a quiet room. If that basketball represents the physical volume of our Sun, the star at the center of TRAPPIST-1 would be roughly the size of a standard golf ball. Now, imagine 7 grains of sand or tiny apple seeds circling that golf ball. This is the delicate miniature reality of the system we are exploring. Observe the way these tiny seeds are arranged. On Earth, we sit at a comfortable distance of approximately 93 million miles from our Sun, a measurement scientists call 1 astronomical unit, or AU. In stark contrast, the innermost planet of this red dwarf, TRAPPIST-1b, orbits at a distance of just 0.011 astronomical units. That is barely over 1 million miles away from its star's surface. Even the furthest planet in the sequence, TRAPPIST-1h, sits at a microscopic 0.06 astronomical units, which equates to roughly 5.5 million miles. You could fit the orbits of all 7 of these planets comfortably within the gap between our Sun and Mercury. Notice how this proximity transforms the night sky. The gap separating Planet B and Planet C is an astonishingly narrow 400,000 miles. Compare that to our own celestial backyard. The average distance from the Earth to the Moon is about 238,900 miles. This means the empty space between these two completely independent Earth-sized worlds is less than twice the distance from your porch to our Moon. If you were resting on the dusty surface of TRAPPIST-1b, Planet C would hover above you, not as a distant twinkling speck, but as a textured, magnificent sphere, dominating the sky with its looming presence. What's happening now as you mentally stand on this foreign soil is a profound shift in sensory input. Because the star is so dim and emits energy mostly in the invisible infrared spectrum, the physical light reaching these planets is incredibly muted. Scientists measure this brightness in a unit called illuminance. On the middle planet, TRAPPIST-1e, the amount of visible light showering the surface is only a tiny fraction of what we experience on a sunny afternoon. The ambient illumination at high noon on Planet E would perfectly match the soft, diffuse glow of a heavily overcast winter afternoon on Earth, just moments before the sun slips below the horizon. It is a world wrapped in an unending, peaceful dusk. Visualize what might grow in that eternal twilight. On our home world, plant life utilizes photosynthesis, a biological process tuned to absorb the visible light spectrum between 400 and 700 nanometers. This specific absorption pattern is what makes our leaves appear green, as they reflect the green wavelengths back to our eyes. However, the TRAPPIST-1 star's energy peaks at around 900 nanometers. For any hypothetical flora to survive in this dim reddish environment, it would need to absorb every single scrap of available visible light to produce energy. As a result, astrophysicists hypothesize that vegetation here would not be green at all. Instead, leaves and forests would appear pitch black, or perhaps a deeply saturated inky violet. Picture a silent, sprawling forest of black silhouettes, calmly drinking in the invisible warmth of a glowing red sky. At this very moment, imagine taking a physical step through that obsidian forest on the surface of TRAPPIST-1d. This specific planet is the lightest of the 7, weighing in at precisely 0.388 times the mass of Earth. Its gravitational pull is almost identical to that of Mars, which sits at roughly 38% of Earth's gravity. Sink into the physical reality of that number. If an astronaut who weighs 150 pounds on Earth were to step onto the soil of TRAPPIST-1d, they would instantly weigh only 58 pounds. The sensation would be one of profound relief and unburdening. It would feel exactly like taking off a heavy, soaking wet winter coat after a long walk through the snow. Your joints would decompress, your muscles would relax, and every movement would become light, effortless, and graceful. The persistent, heavy pull of Earth is gone here, replaced by a gentle, permissive gravity that simply cradles you against the ground. Conversely, travel outward to TRAPPIST-1g, the largest sibling of the system. This world has a radius 1.12 times that of Earth and boasts a total mass 1.32 times heavier than our home planet. Here, the gravity would feel slightly firmer, anchoring you with a comforting, steady pressure. It would feel akin to resting under a weighted blanket, a reassuring embrace from a massive terrestrial sphere, keeping you entirely grounded and secure. Deep within the mechanics of these worlds lies another fascinating geological concept. Due to the tidal locking we explored earlier, The distribution of temperature creates a phenomenon astrophysicists refer to as an eyeball planet. Imagine a world where the substellar point, the exact location where the star shines directly overhead, is hot enough to maintain a vast liquid ocean. As you travel away from that singular warm center toward the eternal night side, the temperatures plummet drastically. Because water freezes at 32 degrees Fahrenheit, the entire dark hemisphere of this planet would be encased in a permanent solid shell of ice, potentially miles thick, much like the subterranean glaciers of Antarctica. From space, the planet would literally resemble a giant eye, a dark, liquid pupil of an ocean staring perpetually at its sun, surrounded by the blinding white sclera of global ice. The transition ring between the liquid and the ice, the Terminator line, would feature a slow, continuous melt, feeding the central ocean in a perfectly balanced, never-ending cycle. To gather this incredibly specific data, humanity has deployed instruments of staggering precision. When the James Webb Space Telescope analyzes these atmospheres, it uses a technique known as transmission spectroscopy. As starlight passes through the thin atmospheric halo of a transiting planet, different chemical elements absorb specific wavelengths of light. By examining the light that makes it through, scientists can determine exactly which gases are present. Recent transmission spectroscopy of the inner TRAPPIST-1 planets sought out signatures of hydrogen and helium. In our own solar system, massive gas giants like Jupiter and Saturn are defined by their thick, primordial envelopes of these two ultralight elements. The data returned from the TRAPPIST-1 system revealed a complete lack of puffy, hydrogen-rich atmospheres around these terrestrial worlds. This is a crucial detail. It tells us that these planets are mature and evolved. The stellar winds of their host star have gently blown away any light, primordial gases over billions of years, leaving behind solid, compact spheres of rock and metal. They are not chaotic gas clouds. They are stable, seasoned grounds. There is another invisible boundary hidden within this system, in a threshold astronomers call the frost line, or the snow line. In any stellar system, this is the precise distance from the star where the ambient temperature drops low enough for volatile compounds, like water, carbon dioxide, and ammonia, to condense into solid ice grains. In our solar system, the frost line sits nearly 5 astronomical units away from the Sun, resting quietly in the cold expanse near the orbit of Jupiter. But scale everything down to our golf ball and apple seeds. In the TRAPPIST-1 system, the frost line is pulled incredibly close to the star. It hovers right around the orbital path of planets D and E, at roughly 0.02 to 0.03 astronomical units. This invisible ring of frost marks the dividing line between the dry, baking inner worlds and the icy, water-rich outer worlds. It is a beautiful silent perimeter, a delicate ring of freezing temperatures that dictates the geology of everything that crosses its path. Observe the harmony in these everyday comparisons, the winter coat of gravity being lifted from your shoulders, the soft living room dusk of an alien high noon, the golf ball star warming its tiny ancient family. Everything in this pocket of the Aquarius constellation scales down into something deeply intimate, manageable, and serene. It is a pocket-sized solar system operating with flawless clockwork precision, inviting us to simply float beside it, unburdened by mass, observing the quiet perfection of the physics at play. Reflect on the delicate biological threads that bind our own existence to the mechanics of the cosmos. As we observe the quiet, predictable clockwork of this planetary family, it is deeply comforting to recognize that the same physical laws governing these distant spheres also govern the beating of your heart and the rhythm of your breath. A profound realization awaits when we examine the unbelievably narrow gaps separating these 7 worlds. At their closest approach, the distance between the habitable zone planets, TRAPPIST-1e and TRAPPIST-1f, shrinks to a mere 0.015 astronomical units. Because they are so small and possess lower mass, the energy required to leave their surface is greatly reduced. For instance, the escape velocity of Earth, the exact speed a rocket or object must reach to break free of our gravitational pull, is 11.2 kilometers per second. On the lighter, TRAPPIST-1 planets, that threshold is significantly lower. Astrophysicists note that this combination of low escape velocity and extreme proximity creates a highly active environment for a theoretical process known as lithopanspermia. This is the scientific term for the transfer of biological material, or the basic building blocks of life, between planets via asteroid or meteorite impacts. When a space rock strikes a world, the collision throws dust and debris upward. In our solar system, the distances are so vast that a rock knocked off Mars might drift in the freezing dark for millions of years before encountering Earth. But in this miniature system, computational models estimate that the likelihood of lithopanspermia is anywhere from 100 to 1,000 times greater than in our own planetary neighborhood. Picture an interconnected root system hidden beneath the floor of an ancient forest, so quietly sharing nutrients and life across the damp soil. The TRAPPIST-1 system acts in a remarkably similar way. Studies of orbital dynamics show that the transit times for ejected rocks traveling between these neighboring planets can be as incredibly short as a single decade. Imagine that. A fragment of stone carrying microscopic organic material could complete the journey from one world to the next in just 10 Earth years. This timescale is critical for the survival of biology. We know from experiments conducted on the exterior of the International Space Station that certain terrestrial bacterial spores, such as Bacillus subtilis, can successfully survive direct exposure to the freezing vacuum and radiation of space for up to 6 years. Because the cosmic travel time in the TRAPPIST-1 system is so brief, biological material could easily survive the journey, acting like dandelion seeds caught on a gentle breeze, drifting across the narrow void to seed a neighboring world. The entire planetary system could function as one massive interconnected biological web. To understand life's resilience, we must also look at the challenges it faces. The universe is ancient, and stars change as they age. Observations reveal that red dwarfs, particularly M-type stars like TRAPPIST-1, undergo a volatile youth. For the first billion years of their existence, these ultra-cool stars are incredibly active. They frequently release intense bursts of extreme ultraviolet, or XUV, alongside high-energy X-ray radiation. Current satellite data confirms that the X-ray luminosity of TRAPPIST-1 is surprisingly comparable to our own Sun, despite the red dwarf being a mere fraction of our Sun's physical size. Imagine the microscopic world within you for a moment. The 50 trillion cells making up your human body rely entirely on the stability of a fragile genetic blueprint. Extreme ultraviolet radiation possesses enough localized energy to sever the chemical bonds that hold DNA together. For any biology to emerge and persist on these alien worlds, it requires an atmospheric shield, much like the one that protects your own skin from the harsh glare of a summer afternoon. On Earth, we are sheltered by a stratospheric layer composed of ozone, scientifically designated as the O3 molecule, which naturally absorbs incoming ultraviolet wavelengths. Complex photochemical models applied to the TRAPPIST-1 system suggest an elegant, self-correcting defense mechanism. The intense UV environment of the star's youth could interact with atmospheric oxygen to produce an artificially thick, dense layer of ozone. Additionally, if the planets maintain a liquid iron core spinning deep within their mantles, they would generate a strong magnetic dynamo. This magnetic field acts as an invisible spherical shield, gracefully deflecting the abrasive stellar winds away from the planet's fragile atmosphere. Beneath the surface of these terrestrial worlds, another rhythmic process mirrors the internal warmth of your own physical body. The gravitational relationships in this system are so beautifully complex that the planet's orbits are not perfectly circular. Instead, they possess non-zero eccentricities, meaning their orbital paths are slightly stretched into elliptical shapes. As these planets trace their elliptical paths, their host star's gravity pulls on them with varying strength. When they are closest to the star, the gravitational tug is stronger, and when they are further away, it weakens. This constant rhythmic squeezing and releasing physically distorts the rocky mantle of the planets, a dynamic process called tidal heating. It is an internal friction, not unlike the warmth generated in your muscles when you move or stretch. Within the dark, pressurized depths of TRAPPIST-1e or F, this tidal heating produces immense geothermal energy. In our own solar system, this exact mechanism drives the spectacular volcanoes of Jupiter's moon Io and powers the hidden hydrothermal vents beneath the icy crust of Saturn's moon Enceladus. Deep in the subterranean dark, these geothermal vents could provide a steady, comforting warmth, creating an isolated sanctuary for life, completely untouched by the radiation of the star above. Now, observe the atmosphere, the very breath of a transiting world. The mechanics of wind and weather here function through a wonderfully unique circulation system. On a rapidly rotating sphere like Earth, a phenomenon known as the Coriolis effect twists the global winds, breaking our atmospheric circulation into distinct segmented bands, known to meteorologists as Hadley, Ferrel, and polar cells. This is what creates our complex, swirling storms and prevailing trade winds. However, on a tidally locked planet, staring permanently at its star, the rotational speed is incredibly slow, resulting in a remarkably weak Coriolis force. Without that twisting momentum, the planet breathes in a single, massive, uninterrupted flow. The central area facing the star, called the substellar point, absorbs the maximum amount of thermal energy. The heated air becomes less dense and rises miles into the upper atmosphere. From there, it flows outward in a continuous, globe-spanning current, traveling all the way to the freezing night side, where it cools, sinks, and flows back across the surface toward the light. It is a singular planetary respiratory system, an endless cycle of inhaling the warmth of the day and exhaling it into the cold of the night. This grand atmospheric conveyor belt acts to equalize the temperatures, preventing the day side from boiling and the night side from freezing solid. It ensures a stable, temperate environment at the twilight boundary, a delicate equilibrium maintained entirely by the steady physics of thermal expansion. Even as these 7 planets orbit their star, the entire system is undertaking its own majestic journey through the cosmos. The TRAPPIST-1 family is located within the Orion arm of the Milky Way, our own galactic neighborhood. Yet, it is not stationary. Astronomers meticulously track the movements of stars to understand the shifting architecture of the galaxy. Measurements show that TRAPPIST-1 has a radial velocity of roughly -56.3 kilometers per second, In astronomical terms, a negative radial velocity indicates that the object is moving toward the observer. At this very second, the red dwarf and its 7 ancient perfectly synchronized planets are gently moving closer to our solar system at over 56 kilometers every single second. Do not view this as an impending collision, but rather a slow, a silent drifting together across the unimaginable depths of the void. Over a human lifetime, the distance it closes is a microscopic fraction of a light year. It is a peaceful, persistent approach. We are sharing the same gravitational ocean, floating through the same quiet sector of the galaxy. The physics that warms their hydrothermal vents, the photochemical reactions that weave their ozone layers, and the thermal currents that drive their eternal winds are identical to the forces shaping our own beautiful world. You are bound to this ancient system by the universal laws of nature, grounded in a reality where every movement, every orbit, and every passing era is perfectly measured and endlessly calm. Step onto the firm, solid ground of TRAPPIST-1e and allow your senses to recalibrate to the mechanics of a truly alien environment. Of all the worlds in this tight-knit family, precise measurements show that Planet E is the most similar to our own home in terms of physical composition. Scientists discovered that its overall density is approximately 5.65 grams per cubic centimeter. When you compare this to Earth's density of 5.51 grams per cubic centimeter, you understand that this world is overwhelmingly rocky and stable. Deep within its structure, models indicate it houses a dense iron core, making up roughly 50% of its total radius, perfectly echoing the 53% core fraction of Earth. Picture this planetary interior like a massive cooling cosmic geode, wrapped in thick mantles of compressed silicate. Observe the sky stretching out above you. You might expect to see a familiar canopy of azure, but the physical laws of light dictate a much different visual reality here. On Earth, our sky appears blue due to a phenomenon known as Rayleigh scattering, where molecules of nitrogen and oxygen scatter the short, energetic blue wavelengths of sunlight in every direction. However, the ultra-cool red dwarf at the center of the TRAPPIST-1 system emits almost entirely in the long wavelength infrared and deep red spectrum. It produces almost zero blue light. Therefore, even if Planet E possesses a nitrogen-rich atmosphere identical to our own, there are no blue photons available to scatter. Instead, the sky above you would appear as a luminous, hazy pale yellow, or perhaps a soft, pearlescent white, glowing warmly under the steady crimson sun. Notice how the surface beneath your feet reacts to this light. Miscalculations suggest that the rocky, cloudless regions of these planets possess a very low bond albedo, sitting somewhere between 0.0 and 0.1. Bond albedo is a scientific measurement of how much total electromagnetic energy a planetary body reflects back into space. A value near zero means the surface is highly absorptive, drinking in almost 90 to 100% of the starlight that touches it. The rocks would appear deeply matte, absorbing the star's energy like dark basalt baking in a desert afternoon. What's happening now as you stand on this absorptive rock is a unique physical sensation of warmth. Human skin contains specialized nerve endings called thermoreceptors, which are highly attuned to detecting infrared radiation. While your eyes cannot physically see the peak wavelengths emitted by this red dwarf, your body would absolutely feel it. The ambient heat would radiate against your skin with the gentle, pervasive pressure of an open oven door across a quiet kitchen. It is an invisible, enveloping warmth that bypasses the visual spectrum entirely, communicating directly with the tactile receptors in your hands and face. Listen closely to the silence of this world and recognize that the very physics of sound would transform around you. The speed of sound is not a constant. It is entirely dependent on the density and composition of the medium it travels through. On Earth, at sea level, acoustic waves propagate through our air at roughly 343 meters per second. But suppose you travel to one of the neighboring TRAPPIST worlds with a thicker, heavier atmosphere, composed largely of carbon dioxide. In a dense carbon dioxide envelope, acoustic waves encounter higher molecular resistance, slowing the speed of sound down to approximately 267 meters per second. Because carbon dioxide is a heavy, sluggish molecule, it also fundamentally alters pitch. The gas acts as an acoustic filter, rapidly absorbing high-frequency sound waves while allowing lower frequencies to pass. Any noise made here, a rock tumbling down a cliff, or the rush of atmospheric wind, would sound incredibly muffled and bass-heavy. Imagine the sensation of listening to a heavy stone rolling across a sandy riverbed while completely submerged underwater. That deep, muted thud is exactly how the alien atmosphere would carry sound to your ears, softening the sharp edges of every noise into a gentle, rhythmic hum. Breathe in the theoretical atmosphere, exploring the chemistry born of ancient geology. To maintain a stable climate over billions of years, a planet with liquid water relies on a geological thermostat known as the carbon silicate cycle. Over vast stretches of time, carbon dioxide is drawn out of the air, bound into surface rocks, subducted into the mantle, and eventually returned to the sky through volcanic outgassing. Billions of years ago, the tidal heating within these planets generated staggering temperatures, creating global magma oceans that exceeded 1,500 degrees Celsius. While those oceans of molten rock have long since cooled into solid crusts, the deep volcanic vents still actively outgas crucial molecules. One of these primary emissions is hydrogen sulfide, a molecule denoted chemically as H2S. The human olfactory system is astoundingly sensitive to this specific compound. We can detect it at concentrations as microscopic as 0.00047 parts per million. If you could safely scent the air on a geologically active TRAPPIST world, you would detect the distinct, earthy aroma of struck matches or a geothermal hot spring. It is the heavy, ancient scent of planetary machinery, churning miles beneath your feet, quietly regulating the atmospheric pressure. Look toward the twilight horizon, where the eternal sunset meets the permanent night. Here, the sky might be painted with an unimaginable light show. Astrophysical models estimate that the dynamic pressure of the stellar wind, the stream of charged particles constantly blowing off the red dwarf, is anywhere from 1,000 to 100,000 times stronger than the solar wind Earth receives. When this massive torrent of charged plasma collides with the magnetic field of a planet, the particles are funneled downward into the atmosphere, creating brilliant auroras. Consider the sheer scale of this interaction. When these charged particles strike oxygen molecules high in the atmosphere, they impart energy, placing the oxygen into an excited state. As the molecules calm back down, they release that stolen energy as visible photons of light. An excited oxygen molecule consistently emits light at very specific wavelengths, precisely 557.7 nanometers, which produces a brilliant emerald green, and 630 nanometers, which yields a deep, vibrant ruby red. Due to the overwhelming strength of the stellar wind and the close proximity of the planets, these auroral ovals would not be confined to the tiny polar caps as they are on Earth. The magnetic topology could stretch and distort, pulling the glowing ribbons of green and red light all the way down to the planetary equator. The sky would ripple with a continuous global curtain of bioluminescent colors, casting soft, shifting shadows across the twilight landscape. Now, transition your awareness outward to the colder, water-rich siblings of the system, TRAPPIST-1F and TRAPPIST-1G. At these further distances, mass radius calculations suggest the presence of staggering amounts of water. Rather than rocky continents, you would find global oceans of unimaginable depth. As you plunge mentally beneath the surface of these alien seas, the pressure increases exponentially with every passing mile. Deep within the crushing blackness of these oceans, the physical state of water undergoes a radical transformation. In our daily lives, Sanwa, we know that water boils at 100 degrees Celsius and freezes at 0, but phase changes are governed by pressure just as much as temperature. At the bottom of these immense global oceans, the crushing weight of the water column exceeds 30,000 atmospheres of pressure. Under this extreme physical burden, liquid water is violently compressed until its molecules are forced to lock together into a rigid crystalline lattice. This creates an exotic high-pressure state of solid water, known to physicists as Ice 7. The bizarre and beautiful truth of Ice 7 is that it remains completely solid, even at temperatures soaring above 100 degrees Celsius. Imagine standing on a dark ocean floor made entirely of this hot ice. It is a solid crystalline bedrock, born purely of gravitational weight, in completely defying our earthly intuition of what ice should be. This deep, pressurized foundation provides a silent, unmoving floor beneath the endless churning of the global ocean above. Everything you can sense in this system, the pale, hazy skies, the muffled underwater acoustics of the thick air, the invisible infrared warmth, the heavy scent of deep geology, and the hot crystalline ice, is a testament to the boundless creativity of physics. The universe simply takes the exact same building blocks we have on Earth, iron, oxygen, water, and carbon, and places them under different physical pressures, under a dimmer, redder light. There is an overwhelming tranquility in understanding the why behind these phenomena. Nothing is random. Everything is a precise reaction. The slowing of a sound wave, the scattering of a photon, and the crystallization of water at extreme depths are all flawless executions of natural law. As you absorb these sensory details, allow the predictable, logical beauty of these chemical reactions to settle your mind, trusting in the endless, quiet stability of the physical universe. We now begin our gentle return, stepping back from the twilight edge of this alien world to view the TRAPPIST-1 system in its magnificent clockwork entirety. As we slowly pull away, the red dwarf and its 7 terrestrial spheres shrink into a single cohesive unit of quiet perfection. To truly grasp the profound peace of this cosmic neighborhood, we must examine the step-by-step process of its distant future, a timeline so expansive it defies earthly comprehension. The longevity of a star is entirely dictated by how it processes its internal fuel. In massive stars like our Sun, hydrogen fusion occurs only in the superheated core, but the TRAPPIST-1 star operates through a fundamentally different, highly efficient mechanism known as full stellar convection. The process unfolds gradually over millennia. First, the dense fusing hydrogen in the core generates intense heat. This thermal energy causes the internal plasma to rise slowly toward the surface. As it reaches the cooler exterior, the plasma releases its energy, cools, and then sinks steadily back down into the core. This continuous churning loop acts like a gentle cosmic stirring spoon, mixing the star's hydrogen and helium completely. Because of this thorough convection, the star does not build up a dead core of helium. Instead, it will gradually consume nearly 100% of its available hydrogen fuel. Compare this to our Sun, which will only fuse about 10% of its hydrogen before expanding into a red giant. Through this slow, meticulous process of convection, astrophysicists calculate that TRAPPIST-1 will continue to burn steadily for up to 12 trillion years. It is a beacon of absolute endurance. Observe how this massive timeline interacts with the shifting architecture of the galaxy. The TRAPPIST-1 system is not stationary. It is engaged in a continuous journey across the Milky Way. Astronomers measure its proper motion, the gradual shift of its position across our sky, at precisely 1.04 arcseconds per year. Following this trajectory, it orbits the galactic center, completing one full revolution approximately every 225 to 250 million years, a duration scientists call a cosmic or galactic year. As this slow procession continues, our local universe will undergo a dramatic transformation. In roughly 4.5 billion years, our Milky Way galaxy will physically collide and merge with our nearest galactic neighbor, the Andromeda Galaxy, also cataloged as M31. During this colossal event, the gravitational forces will warp spiral arms and fling billions of stars into new trajectories. Yet, the TRAPPIST-1 system will remain entirely unbothered. Because all 7 of its planets are packed so incredibly tight, occupying a space of less than 0.06 astronomical units across, their gravitational bond to their red sun is phenomenally strong. The process of galactic merging will simply sweep around them, leaving their intimate orbital dance perfectly intact. The mechanism maintaining that dance is equally precise. The Laplace resonance holding these planets together functions as an automatic, self-correcting process. If an outside force, perhaps a passing comet or a minor asteroid impact, nudges one of these planets slightly out of alignment, a fascinating sequence begins. First, the planet's orbital speed alters by a fraction of a second. Then, as it approaches its neighboring planet, the gravitational pull of that neighbor acts as a gentle tether. Over the course of several thousand orbits, this tether incrementally pulls the wandering planet back into its exact mathematical slot. It is an intricate step-by-step orbital healing process, guaranteeing that the 8:5:3 ratio remains flawless for billions of years. As the star eventually ages trillions of years from now, it will undergo a profoundly peaceful transformation. Once the final atoms of hydrogen are fused, the convection process will halt. The star will slowly compress under its own gravity, heating up slightly to become a theoretical object known as a blue dwarf. Following this phase, it will shed its remaining heat, transitioning into a white dwarf. Finally, it will spend quadrillions of years gradually cooling into the absolute dark, slowly matching the temperature of the cosmic microwave background radiation, which will eventually rest near absolute zero, or precisely 0 Kelvin, which equates to minus 273.15 degrees Celsius. Bring this vast unfolding timeline back to your own physical form. The connection between the cooling of ancient stars and the beating of your heart is not merely poetic. It is a verifiable biological process. Trace the sequence of your own creation. Before our solar system existed, massive ancient stars went through their own life cycles. Deep in their cores, a process called stellar nucleosynthesis forged heavy elements. When those stars exhausted their fuel, they collapsed and rebounded in violent supernova explosions, scattering these newly minted elements across the interstellar medium. You are the direct result of that exact process. Oxygen, the element keeping you alive in this very moment, makes up exactly 65% of your total human body mass. Every single atom of that oxygen was fused in the crushing pressure of a dying star. Carbon, the foundational building block of your cellular structure, accounts for roughly 18.5% of your mass. Calcium, constructing the quiet strength of your bones, makes up 1.5%. Most intimately, consider the iron in your blood. An average adult human body contains approximately 4 grams of elemental iron. This specific metal binds with oxygen in your hemoglobin, allowing your circulatory system to function. The sheer thermal energy required to fuse iron does not exist during a star's normal life. It is only forged in the final multi-billion degree milliseconds of a core collapse supernova. The iron carrying oxygen to your brain right now traveled through the freezing vacuum of space for billions of years before settling into the Earth and eventually into you. You are a biological extension of the cosmos, forged in the exact same enriched stellar nurseries that built the rocks of the TRAPPIST-1 planets. As you internalize this profound physical connection, invite the sensation of rest to mirror the quiet mechanics of the universe. The descent into sleep is its own graceful, step-by-step biological process. First, in response to the dimming light of your environment, a tiny structure deep within your brain, called the pineal gland, begins to actively secrete a hormone called melatonin. This chemical signal travels gently through your bloodstream, whispering to your 50 trillion cells that the time for wakefulness has passed. Next, your physical structure begins a process of thermal regulation. To initiate the deepest stages of rest, your core body temperature systematically drops by approximately 1 to 2 degrees Fahrenheit. This gradual cooling mirrors the transition of a transiting planet slipping quietly behind its star, entering the cool, protective shadow of the night. As your body cools, the electrical activity in your brain transitions. The rapid, high-frequency beta waves of your waking hours gradually stretch out, smoothing into the slow, rhythmic rolling of delta waves. These delta frequencies oscillate at a calm, deliberate pace of just 0.5 to 4 hertz. It is the exact same slow, predictable rhythm as a planet tracing its elliptical path through the dark. Simultaneously, a remarkable physical cleansing begins. Deep inside your nervous system, the glymphatic network engages its nightly cycle. The interstitial space between your brain cells physically expands by up to 60%. Into this newly opened space, cerebrospinal fluid flows steadily, gathering and expelling metabolic byproducts, such as beta-amyloid proteins, that have accumulated throughout the day. Where this physiological process restores your mind with the same silent efficiency as the planetary winds equalizing the temperature on a tidally locked world. Everything is operating exactly as it is designed to. The universe moves in perfect measurable steps, and so do you. From the slow fusion of hydrogen in an ultra-cool red dwarf to the careful dropping of your core temperature, you are a masterwork of natural law. Permit your mind to finally surrender the heavy gravity of the waking world. Release the tension in your muscles, step by step, starting from the crown of your head, flowing down through your shoulders, your chest, and releasing entirely through the soles of your feet. You are safe. You are anchored to the quiet logic of the cosmos. Accept these truths as you drift into the absolute stillness. And I am completely at peace in this moment. My body is a quiet reflection of the stars above. I breathe in harmony with the ancient rhythms of the universe. I am made of stardust, safe in the dark, held by the gentle forces of nature. I release the events of the day, trusting the slow turning of the earth. My mind is clear, my body is heavy, and my spirit is endlessly calm. I belong to the silent, comforting void. I am entirely ready to rest. Good night.